Now let us consider a simple example. Consider the Galton-Watson process Zn with offspring distribution Pk. Assume that P0 is equal to 1 by 5, P1 is equal to 3 by 5 and P2 is equal to 1 by 5. So this is the probability mass function for the random variable Z1. Our interest is to find out the conditional probability P, probability of Z2 is equal to 3 given Z1 was 2, and also probability that Z2 is equal to 2 given Z2 was 3, and also what probability of Z2 is equal to 2. So the conditional probability P Z2 is equal to 3 given Z1 is equal to 2, that is same as probability of Y1 plus Y2 equal to 3. That is possible either Y1 is equal to 0 or Y2 is equal to 3, or Y1 is equal to 1, Y2 is equal to 2, or Y1 is equal to 2 or and Y2 is equal to 1, or Y1 is equal to 3 and Y2 is equal to 0. Since YAs are IID random variables, you can write down this as a probability of Y1 is equal to 0 into probability of Y2 is equal to 3 and so on. Probability of Y1 is equal to 0, that is nothing but P0. Probability of Y2 is equal to 3, that is nothing but P3. Similarly, the second expression is P1 into P2, third one is P2 into P1, the last one is P3 P0. Since P3 is equal to 0, the first term and the last term will be 0. So you will get P1 P2 plus P2 P1, that is same as 6 by 25. So this is the conditional probability of P of Z2 is equal to 3 given Z1 is equal to 2. Similarly, one can find P of Z3 is equal to 2 given Z2 is equal to 3. That is possible when Y1 plus Y2 plus Y3 is equal to 2. So the probability of Y1 plus Y2 plus Y3 is equal to 2, we have 6 possibilities. Substitute the value of P0, P1, P2, you will get the numerical value of this conditional probability. Similarly, one can find the probability of Z2 is equal to 2 also. Probability of Z is equal to 2 is same as probability of Z2 is equal to 2 given Z1 is equal to 0 multiplied by probability of Z1 is equal to 0 plus the combination with the probability of Z1 is equal to 1, probability of Z1 is equal to 2. Substitute the values, then you will get the probability of Z is equal to 2. Now we are going to discuss the probability generating function for the branching process. Let YI's be IID random variables, each having the same distribution like Z1. Let H of S be the probability generating function of YI's. Let Hn of S be the probability generating function of Zn. Since Z0 is equal to 1, you will get H0 of S is same as S. Now our interest is to find out the probability generating function for Z1. That is same as the probability generating function of YAs. The probability generating function of YAs is H of S, therefore H1 of S is same as H of S. Our interest is to find out the probability generating function for Zi, Zn, where n is 1, 2, 3 and so on. This we are going to give it as a theorem. Hn of S, this is nothing but the probability generating function for the random variable Zn is same as H of n minus 1 of h of s, and hn of s also can be written in the form of h of hn minus 1 of s. Let us see the proof for this. You know that probability of Zn is equal to k, that is nothing but summation over i's probability of Zn is equal to k given Zn minus 1 is equal to I multiplied by probability of Zn minus 1 is equal to I. You know that this conditional probability is nothing but probability of y1 plus y2 and so on plus yi is equal to k multiplied by probability of Zn minus 1 is equal to I. Now we will go for finding out the probability generating function for the random variable Zn. Substitute probability of Zn is equal to k from above in this equation. Therefore, you will have a summation of k, substitute the probability of Zn is equal to k, that is nothing but the summation over I, probability of conditional probability multiplied by probability of Zn minus 1 is equal to I multiplied by s power k. Substitute the conditional probability is nothing but the probability of y1 plus y2 plus so on yi is equal to k into s power k. Since yi's are IID random variables and the probability generating function of yi's are nothing but h of s, the probability generating function of sum of I random variables yi's, that is nothing but h of s whole power I, because of yi's are IID random variables and the probability generating function of yi is equal to h of s. Therefore, the probability generating function of y1 plus y2 and so on plus yi is h of s whole power I. Therefore, substitute this is nothing but the probability generating function of y1 plus y2 plus and so on plus yi. Therefore, hn of s is nothing but summation over k, hn of s is nothing but summation over I probability of Zn minus 1 is equal to I times h of s whole power I. Replace this by h of s whole power I. Therefore, summation I probability of Zn minus 1 is equal to I h of s whole power I. So, that is nothing but the probability generating function for the random variable Zn minus 1 with the replacement s by h of s. Therefore, hn of s is nothing but hn minus 1 of h of s. So, the first part is proved. Hn of s is same as hn minus 1 of h of s. Now, we are going to prove the second part. We know that h1 of s is h of s, that is same as h of h naught of s, because h naught of s is nothing but s. Suppose this is true for n is equal to j, that means h of j of s is h of j minus 1 of s, then we can find out what is h of j plus 1 of s. That is nothing but hj of h of s, that is same as h of j minus 1 times h of s, that is same as h of j of s. By induction, it is proved. Now, we are finding the moments of Zn. Let mu is equal to expectation of Z1 and sigma square is nothing but the variance of Z1, then expectation of Z of n, that is mu power n, and the variance of Zn will be, for mu equal to 1 it is n times sigma square, for mu is not equal to 1 it will be mu power n minus 1 times mu n minus 1 times sigma square divided by mu minus 1. We will prove the part 1, that is expectation of Zn is equal to mu power n. By theorem 1, you know that Hn of S is same as Hn minus 1 times, by theorem 1 we know that Hn of S is Hn minus 1 of H of S. Then differentiating and putting S equal to 1, we will get Hn dash of 1, that is same as Hn minus 1 dash of H of 1 into H dash of 1. We know that H of 1 is 1, H dash of 1 is mu. Therefore, for n is equal to 1, 2 and so on, you will get Hn dash of 1 is same as Hn minus 1 dash of 1 into mu, that is same as Hn minus 2 dash of 1 into mu square and so on. Therefore, you will get mu power n, because you know that H dash of 1 is mu. By recursively, you will get Hn dash of 1 is mu power n. Therefore, expectation of Zn is nothing but Hn dash of 1, that is same as mu power n. So, till now we have discussed the probability generating function of Z power n, and also we have discussed the mean and variance of Z of n. As a remark, if mu is equal to 1, the expectation of Zn tends to 1, whereas the variance of Zn tends to infinity as n tends to infinity. You can see it from this theorem. As mu tends to 1, expectation of Zn will tends to 1, whereas the variance tends to infinity, because that is same as n times sigma square. Therefore, as mu tends to 1, the variance of Zn tends to infinity as n tends to infinity. Whereas if mu is less than 1, the expectation of Zn tends to 0, and the variance of Zn will be sigma square divided by 1 minus mu as n tends to infinity. Similarly, if mu is greater than 1, then the expectation of Zn will tends to infinity, and the variance of Zn tends to infinity as n tends to infinity. This also you can see it from the theorem. Now we are going to discuss the criticality. A very important classification is based on mean, progeny, count, mu is equal to expectation of Z1. A very important classification is based on the mean, progeny, count, mu is equal to expectation of Z1. You know that expectation of Zn is equal to mu power n. Just now we have proved it in the theorem 1. Therefore, in the expected value sense, the process grows geometrically if mu is greater than 1, stays constant if mu is equal to 1, and decays geometrically if mu is less than 1. From the expectation of Zn is equal to mu power n, we can conclude if mu is greater than 1, the process grows geometrically. If mu is equal to 1, then the process stays constant, whereas if mu is less than 1, the process decays geometrically. Thus, three cases are called supercritical, critical and subcritical respectively. That means if mu is greater than 1, then the process is called supercritical. In this case, the expectation of Zn tends to infinity. When mu is equal to 1, the process is called critical, and expectation of Zn is equal to 1 as n tends to infinity. When mu is less than 1, the process is called subcritical, and expectation of Zn will tends to 0 as n tends to infinity. Now we are going to consider The second example, consider the Galton-Watson process Zn with offspring distribution Pk. We choose the same problem, example 1, with the assumption P naught is equal to 1 by 5, P1 is equal to 3 by 5 and P2 is equal to 1 by 5. Now we can find out the mean of Z1, that is nothing but 1, because P naught is equal to 1 by 5, P1 is equal to 3 by 5, P2 is equal to 1 by 5, we will get mean of Z1 will be 1. Hence, this process is called a critical Galton-Watson process, because mu is equal to 1. You can find out the variance of Z1 also. First, you find out expectation of Z1 square, that will be 7 by 5. Hence, variance equal to expectation of Z1 square minus expectation of Z1 whole square, that will be 2 by 5.